a decimal number into hexadecimal and vice versa, we're going to move on to the conversion of binary into hexadecimal and vice versa. So in the last lecture I taught you how to convert a binary number into decimal and vice versa. It is quite similar when it comes to hexa, but there's a catch when it comes to hexadecimal. In order to convert a hexadecimal number into binary, you have to have an intermediate state which will look something like this. A hexadecimal number has to be converted first into decimal number and then to binary, and same goes in return. You have to convert a binary number into decimal and then convert that decimal number using the methods taught before into hexadecimal. Now you can write in the comments if you want me to teach the full method, but because instead in this video I'm going to teach you a shortcut method which will help you convert a hexa number directly into binary and a binary number directly into hexadecimal. Now it is slightly you can say combination of concepts without the deeper knowledge of them, but we're going to use that because it makes our work quite faster and easier. Firstly, we're going to look at a hexadecimal number. A hexadecimal number, let's say we can use an A, B, C, 3. Alright, so let's say we have a hexadecimal number. Alright, let's write 16 here. Now what I want you guys to do is I want you guys to write them out separately like this: A, B, C, D. Okay, and now I want you to write these numbers under each of the hexadecimal word. Oh wait, my bad, this is not a D, this is a 3. Yeah, sorry. Okay, so I want you to write these numbers under each of the characters: 1, 2, 4, 8, 1, 2, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. Now what these are basically powers of 2, starting from 0 up until 3. Starting from 0 up until 3. 0 up until 3. Now what you're going to do afterwards is you're going to choose the numbers that when added make up this top number. Like if you pick up 2 and 1, adding them will give you 3. So what you'll do is you'll pick these two numbers by putting a 1 on top of them like this, and then you'll put the remaining zeros in that set. This becomes a set of 4 binary numbers. Okay, now you'll keep repeating that. For assistance, we'll have this table right here so we can work better. We've got an A equal to 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So okay, so a C is 12, so we basically have to make a 12 using these 4 numbers, which we can do by choosing 8 and 4, because 8 plus 4 gives you 12, and we'll put the remaining zeros in the set. As for B, we have 11. 8 plus 2 plus 1 gives you 11, and you'll put the remaining 0. And then you have A, which is 10. 8 plus 4 gives you 10, and the remaining zeros will be substituted. Now you can see that this is the binary number you want. Let's write it out cleanly. We've got a 1 0 1 0 1 0 1 1 1 1 0 0 0 0 1 1. This is the binary number equivalent to your A, B, C, 3. Now we're going to look at conversion from binary to hexadecimal. So let's take a sample binary number. Let's choose a bigger one so we can have more hexadecimal characters. Let's choose let's say 12-bit binary number, or maybe 13. Let's do 13. So we've got 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Oh, let's do 14. Okay, let's erase the last 0. Okay, So before we start converting any binary number into hexadecimal with this method, I want you guys to make sure that you have each set of four binary characters. 4 4 4. Here you can see that we have a single one remaining. Now what you'll do is you'll add 3 zeros in the back to make it a complete set of 4. Remember that however many zeros you add before a binary number, they don't have any weightage, so they don't change the true meaning or the true count of the number. Okay, so now you have 4 sets of 4-digit binary numbers, and what you'll do now is repeat what we did in the previous process. You'll be writing powers of 2 starting from 0 to 3 backwards. 1 2 4 8 1 2 4 8 1 2 4 8 1 2 4 8. And now what you'll do is, after you've written these, you'll be choosing the number with a 1 on top of this, which in this case is this. You'll choose 1. Okay, in the second set what you'll do is you have 8, and you'll add all the other numbers that have a 1 on top of them, which is a 2. In this you have 8 plus 4 plus 2, because these three have a 1 on top of them. In the last set you have 4 plus 2 plus 1, because these three have a 1 on top of them. Now what you'll do is you'll evaluate them. 8 plus 2 gives you 10, 8 plus 4 plus 2 gives you 14, 4 plus 2 plus 1 gives you 7. Now all the numbers that are higher than 9, because we know hexadecimal only can represent 9 as the highest number, will be converting all the higher numbers into alphabets. As we saw above, we've got A as 10, and we've got 14 as E right here. So we'll be substituting the 10 with an A, we'll be substituting the 14 with an E, and we'll write the other ones just as they are, 1AE7, and this is it. This is your hexadecimal number converted from a binary number using the shortcut method. This method also shows us one very essential thing about hexadecimal numbers, which is that each hexadecimal number is equivalent to 4 binary numbers, which is very important because it is going to help us understand that how the computer utilizes hexadecimal number during its processing. Now what happens is, in a typical register you have 16 bits of memory, which means it can store 16 bits. Dividing those 16 bits into groups of 4, we've got 4 groups, which means it will be able to hold 4 hexadecimal numbers. Let's write A. It can be any number. I'm just using this tetra A for simplification purposes. Now before we end the lecture, I'm going to discuss where the hexadecimal number systems are used. So one of the first most important use for hexadecimal will be the storage of memory addresses. An address can consist of 16 bits, which means it can possibly contain 2 raised to the power 16 addresses, and each address can have a unique hexadecimal value to represent it while using it in the assembly language. So you've got your uses for hexadecimal. First will be your color codes in HTML. Color codes, basically you have these sets of values. You've got an R value, G, B. This is a red, you've got a green, and you've got a blue value. Now what these values are means they have the ranges of values from 0 to 255. This representation of 0 to 255 values can take up to 8 bits, or weird R, I can't write today. 8 bits or 2 hex values, which means you can just write F and it will mean 255, or you can write 01 and it will mean 001. You know, a simple one will work too, you see. So let's say you have 255 for red and 33 for green, and let's say a 0 for blue. This will take you this many decimal numbers if you were to write it in decimal, and many more numbers if you were to write it in binary. But instead, when you use hexadecimal, you'll just have to write an FF 21 and a 00, and this will be the total representation of the color in hexadecimal. This is also represented by a hashtag before the number, and it's written like FF2100. So this is what a color looks like in hexadecimal notation when using with HTML or CSS. After colors, you've got your MAC addresses. Now what MAC addresses are, these are machine access codes. Now what machine access codes are they're basically a unique representation for every single device existing on the internet. It can be a computer, cell phone, or any terminal, and each one has its unique ID or address, so it can be accessed and the packets can travel from one address to another. Now, because this address is a huge number or can be a huge number, they have this hexadecimal notation which can be squeezed in and used for more convenience. MAC address can look something like 0, 2, 1, 2, 3, 3, 1, 0, and 10. Now, if we were to convert this into a decimal number or a binary number, it will be a 48-bit number in binary, which is quite a huge amount, because the number of devices that can be represented in that number is 2 raised to the power 48, and you can also see how many characters that will be consuming if we were to represent that in an output form. So that's where hexadecimal numbers are used also. After that, you've got your error codes. You see, when you play a game, it shows you stuff like 0x, you've got a 0x0002 something file not found. See, there can be a lot of error codes, and these error codes are represented in hexadecimal for easier recognition. So you've got your error codes as a potential use for hexadecimal. Then you have your assembly language or machine code. Assembly language, please ignore my handwriting, or machine code. Now what assembly language is it is basically a low-level language that is closer to the machine than it is to the human. What it does is it allows for the user or the programmer to control the actions of a machine at a deeper level than a high-level programming language such as Java or Python, etc. Now you don't have to regard yourself with this, and you can just don't pay a lot of attention if you don't know what it means. I'm going to give you an example of what an assembly instruction looks like. So you've got an MOV with an AH followed by a BB. Now what it means is move the content BB into the upper half or A high byte of the A register. You've got a register A which has a high byte and a low byte. We studied what a byte is. We've got 8 higher bits and 8 lower bits, and a high byte represents the upper ones, and what the command is telling us is to store this BB into this. Now what a BB is can be the number that is in hexadecimal notation. It will be converted into binary, and that binary number will be stored into this AH in the form of zeros and ones. I hope you're clear now. That is all for today. Thank you very much for watching.